Good afternoon, everybody. We'll get started in just 30 seconds here. We have just a few more logging in. Okay, well, good afternoon and welcome everybody. My name is Scott Quillinan. I'm the Senior Director of Research for the School of Energy Resources. And it is my pleasure to welcome and moderate this panel today. So today we'll be talking about rare earth element critical mineral development in Wyoming. The webinar is being recorded. So if you know folks that wanted to sign up but couldn't, this will be posted on our website later today. So they are able to catch up and learn all about it just like you. The other announcement is this webinar was approved for 1.5 hours of CLE credits. So if you need more information on that, please just reach out to us. But we have a great group of speakers today. It's going to spur some interesting questions and discussions around the topic. We'll explore conventional and unconventional sources of rare earth elements and where they lie in Wyoming. We'll also discuss potential market and policy drivers that could be implemented to help drive development in Wyoming. You'll probably also hear that a rare earth element industry is thriving overseas, and creating a domestic industry might be a little tough, and it's not going to be easy, even in a state like Wyoming. But in my opinion, Wyoming has a reputation for being a leader in energy technologies. It's supportive of its mining and extractive industries, and has an urgent need for economic diversification. Plus, and I've been quoted saying this several times, but I'll continue to say it until somebody proves me wrong, but Wyoming is just one of those places where we can really get things done. And I think research and innovation can help us get there. So that's why collaborations like these with industry, national laboratories, universities in the state, it's really a key part to the success. So it's a pleasure to introduce our 5 panelists today. Each panelist will have an opportunity to introduce themselves more thoroughly, so I'll do it briefly here. So today with us, we have Dr. Holly Krupke, Executive Director for the School of Energy Resources. She will be presenting on behalf of Melissa Firestone. Melissa is a natural resource economist here at the School of Energy Resources, but had a family emergency, so she wasn't able to join today. So thank you, Holly, for stepping in. We have Randy Scott from Rare Earth Element Resources, who will talk about an approach to conventional rare earth element deposits. We have Thomas Tarka from the National Energy Technology Laboratories, who will be talking about unconventional sources and extractive technology, or unconventional sources of rare earth elements. Jada Garofalo is a research scientist here at School of Energy Resources, which will be talking about state and national policy surrounding rare earth elements. And then Aaron Phillips is a research scientist here at School of Energy Resources to talk about our approach and opportunities to rare earth element recovery here in Wyoming. So each panelist will have about 10 to 15 minutes for their presentation, and we're going to hold all questions till the end. There's plenty of time for question and answer at the end. So with that, let me get out of the way and introduce our first speaker. So Dr. Holly Krupke, are you ready?
I am. Thank you so much, Scott, and welcome everyone. So as Scott said, I am actually presenting for Melissa Firestone, who did all the work that I'm about to present, and just our thoughts are with her and her family today, as she wasn't able to make it. So please move to the next slide. So what I'll be talking about today will be published as part of a 2-paper series that's going to be posted on our website at the Center for Energy Regulation and Policy Analysis. And we'll send out an announcement on these papers as soon as they're published to everyone who's attending this webinar today. And so the School of Energy Resources and the Center for Energy Regulation and Policy Analysis, who we call SERPA, the goal is to focus on policies and actions supporting Wyoming. And in this particular case, we're focused on what would it take to develop a robust rare earth element supply chain and really an industry here in Wyoming. And to do that, we need to understand where the market is today and where the industry is today. So the comments today are focused on the paper one, which is the global status. And so in that paper, we'll be covering, and in my comments, the unique characteristics of the rare earth element industry and the complexities that characterize the market. We'll also talk a little bit about the overview of the production and extraction processes, and not from a technical perspective in this case, but where they're happening today and how they impact the global market. We'll also do an overview of the global market, and then I'm not going to talk about it too much today, but it is worth mentioning that at both at the federal level and then principally at the federal level, there has been government interest policies proposed and funding directed to the study of developing a rare earth element industry here in the US. And you'll hear about some of that research going on in some of the later presentations. So topics I won't cover today, but will be in our second paper. We'll explore the implications of the market issues and how can we actually build domestic rare earth industry here in the US and in Wyoming. So we'll talk about specific barriers to a supply chain in Wyoming, and quite frankly, there is going to need to be policy support for this industry to stand it up. And so we'll talk about different policy solutions in that second paper. And we'll cover both the proven reserves in Wyoming, such as the Bear Lodge complex, which you'll hear about, or the Bear Lodge deposit, which you'll hear about, and then as well as unconventional sources of rare earths in the state. So next slide, please. So today I want to start talking about, start the presentation with reserves. So reserve data is somewhat limited, but the USGS has the most comprehensive information, and it publishes an annual report on global rare earth element reserves and production, and that is reported out in metric tons of rare earth oxides. It is somewhat limited, the data for global reserves. There are countries that we do know have meaningful reserves that aren't necessarily included. But a couple interesting facts. I mean, rare earth elements are very different from some of the other mining that we're familiar with here in Wyoming. So, for example, the US represents only 1.3% of global reserves, but in 2020, it was estimated to produce 15.5% of global mine production. And this chart on the right-hand side of global reserves starts to demonstrate some of the reason for Chinese dominance in this sector, but doesn't fully explain it. So we're going to get into more details on that. So next slide, please. So now we're going to move into not just reserves, but global production of rare earth elements. And this is characterized by changes over time. In the 1990s is when China really began ramping up its rare earth element industry. And at that time, the US was actually the global dominant global producer. As we try to understand where the industry is today, there are challenges. The USGS data sets on production don't include several sources where we know that production exists. And part of the reason is, for example, REE concentrate. So if the rare earth elements are produced but then changed into a concentrated form, in some Asian countries like Japan, they're not included in estimates. There are REE materials produced in Europe, and then Myanmar heavy REE production isn't included in some of these. So we know that the data is good, but not fully complete. So for our work to try to understand the market, we paired USGS information with the UN Comtrade database, which publishes comprehensive statistics and data regarding international trade between UN member countries across the globe. We found other issues, and of course, UN data does not include non-UN member countries. So we're pairing that with USGS to try to get as good of a picture as we can. But there are issues. In 2020, it was estimated that exports from China to Myanmar totaled 35,000 metric tons, but the UN data showed that number was 0. So we're still working on refining the data to the best of our ability. One other small thing that's worth mentioning is that it's hard to get apples to apples comparisons. So you can look at production of the rare earth elements, you can look at rare earth oxides, you can look at concentrates. So it is complicated to try to understand exactly where the production stands today. So next slide, please. The one thing we do know for sure is that China has dominance over the rare earth element industry and production as a whole. And I think it's fair to say that China's dominance over this sector is both production and refining is due only in part to Chinese strategy. Other countries have exported their industries to China. So government regulation over RE development in China began in 1975 with the inception of the National Rare Earth Development and Application Leading Group. At that time, rare earth production was relatively small, and the government aimed to increase the exports of rare earth elements in 1985 by implementing an export tax reimbursement. And this led to a significant increase in production. And by 1990, production had doubled to about 16,500 metric tons per year. A combination of events in other countries in 1989 and 1990 contributed to further growth. For example, in France, a rare earth element processing plant was denied extension of its radioactive waste disposal permit, and that caused the facility to shutter in France and move to China. During the same period, Japan was also shuttering its rare earth element processing facilities and moving them to China. So at this juncture, the rare earth element industry in China was growing and profitable. However, the ramp up of rare earth element production and operations, and even some illegal operations in China, caused supply to increase rapidly and prices turned negative. And due to the growth in the industry and the impact of illegal production, the Chinese government became much more active in the regulation of that industry. So in 1990, for example, the Chinese government declared RE a strategic resource for the country. And then consequently, it determined it to be a protected resource, which restricted foreign investment. Then in 1991, the Chinese government took over regulation of all steps of production of REE from its ionic clay resources, and only state-owned mining companies were allowed to participate in that production. In addition, only state-owned mining companies could run RE separation and smelting operations. The government executed all trade associated with RE from ionic clay. And from 1991 to 1998, RE production in China increased from that 16,500 metric tons of REOs per year to over 65,000. In 1999, China began employing an export quota that encouraged production of oxides and metals and favored state-owned firms. And then from 2005 to 2010, while China's RE production continued to increase, its exports decreased. And so what we're seeing there is actually the concentration of the full sector, not just production, but the downstream processing, midstream processing, and then using in ultimate products. The export tax, well, I'll talk about that in 1 second. So in 2006, the RE concentrate production quota was instituted that was applied directly to producers. And to further restrict exports in 2007, China started to levy export taxes for all RE ores and downstream rare earth element oxides and metals. The strict export taxes were aimed at incentivizing the downstream sector. The taxes imposed on legal firms created even higher profit margins for illegal production. So the US and other countries ultimately challenged China's export restrictions at the World Trade Organization, and China lost that dispute and subsequently canceled all its export quotas and taxes in 2015. But China does continue to establish production quotas, which have changed over time. But in most recent years, the production quota has grown up to 140,000 metric tons per year in 2020, and the quota was 84,000 metric tons for just the first half of 2021. So annualized, that would be 168,000 metric tons. So in addition to that, the issue of illegal mining in China still needs to be considered when looking at those numbers. So it's widely acknowledged that there continues to be illegal RE production coming from China, and that all has to be considered when looking at this data. In 2016, it was estimated that illegal production represented 25 to 30% of global rare earth element supply. So China's increased government control over production and the midstream sector has led to the current state of the global rare earth mining and concentration market. This market's characterized by upstream. It's more diversified. Production is more diversified in terms of countries. So we saw that in our first graph, that there are many countries actually producing rare earth elements, but the stranglehold on the midstream and downstream parts of the industry continue to be held by China. So go to the next slide, please. So, and an important characteristic, especially where so much production and midstream and downstream, final products are produced in one country, is that pricing information is really challenging to find as well. So, an important characteristic of rare earth elements, unlike other true commodities like gold, coal, oil, is that rare earth elements are not generally end products in and of themselves. They're an essential part of many products we use around the world, like cell phones, televisions, MRI, military guidance, solar panels, cars, wind turbines, and much more. But they're not sold as the initial as an initial commodity. For the energy sector, two of the most important uses include things like catalysts and chemical processing and growing application in magnets. And we do expect, of course, that there will be a surge in demand for rare earth elements based on energy policies around the world, which are particularly important given the recent events at COP. These industries building out a clean energy industry is going to need more rare earth elements, particularly magnets. But the price information is very difficult to find. So there's not much we know about it, but on this slide, you can see a very clear price spike, and that it was experienced in 2011, and it was caused by China's government cutting its rare earth export quotas by 40%. And as I already said, the World Trade Organization ruled against the legality of that export quota, and China lifted the restrictions in 2015. But this shows the level of market control held by one country currently. So it's very important to emphasize that if the US and here in Wyoming, if our goal is to build a robust rare earth element industry and supply chain, it's going to require policy solutions that protect it from price manipulation, price suppression. And China certainly has the ability and has manipulated the market. So it will require intervention. And if you go to the last slide, I would like to thank you all for your time and attention. And we look forward to continuing our work in this to identify specific policies that will help build a robust industry here in the US and in Wyoming. Thank you.
Thank you, Holly, and thank you again for stepping in to cover for Melissa. And we wish Melissa well. So Randy, let's go to you.
Great, Scott. Thank you very much. It's a real pleasure to be with everybody this afternoon. I thank you very much for the invitation to be on the panel today. My name is Randy Scott, and I'm the president and CEO of Rare Element Resources. Rare Element Resources is the company that owns and operates and is exploring and developing the Bear Lodge project near Sundance and in Upton, Wyoming. I've been the president for 10 years now, and during that period of time, we've brought the project forward from a very small exploration target to what we now believe is a world-class resource with a substantial long-lived resource of a mixed rare earth element resource. Excuse me. And During that period of time, we've brought the project forward with regards to permitting as well as development of process technology. I guess you would consider us to be a conventional rare earth resource and project, but there's really not anything that's conventional about the development of our process technology over the last 5 or 10 years. As many of you know, developing, it's great to have a fantastic resource in the ground, but without spending millions of dollars working to improve your process technology, you don't have much. And so in our case, we've done that. We've spent 5, 6, 7 years working on developing process technology. That process technology has now advanced quite nicely, and we are getting ready to move forward with the next big step in the development of the project. So what is that? You probably noticed that over the last month or so, we have received very good news with regards to participating in a large DOE funding activity for the development of a demonstration scale plant associated with the Bear Lodge project. We've spent Rare Element Resources and our consortium of 3 other companies spent over a year in preparing the proposal to the Department of Energy, as well as negotiating the final terms and conditions, cost, scope, et cetera, for the project. It's been quite a ride. And back in about October 5th, a few weeks ago, we were able to announce that we had received financing and the go-ahead on the rare earth demonstration project from DOE. So let me draw a quick distinction, because I did preview some of the questions as well. The project that we're looking at developing here is not the commercial scale operation with full-scale mining and a full-scale plant. Instead, what we have is funding from the DOE to progress from our pilot plant studies through scale up to a demonstration scale plant that is going to process material that we already have extracted and is stored ready to go to feed the demonstration plant. So the project itself consists of an award for $44 million. It's a cost sharing arrangement where the Department of Energy will be providing $22 million towards the total cost of the project, and Rare Element Resources will be providing the other $22 million towards the project as we move forward. The project is expected to last about 40 months, a little over 3 years. The first part of the project, the first period, the first year essentially, is devoted to permitting and final design and engineering for the project. The second period, the second year, then is devoted to procurement of equipment and the construction of the facility itself. Let me say a word about that. The facility is located in Upton, Wyoming. We have obtained a lease on 8 acres at the industrial site there, and includes several already existing brownfield buildings that we will be modifying to hold the new facility for the project. The project, Holly had a couple of interesting points there with regards to supply chain. One of the distinctions, I think, with regards to this project is that we are not intending to produce just a mixed rare earth concentrate. This project is going to produce separated rare earth oxides, and the emphasis specifically is on the production of neodymium, praseodymium oxides, which it was pointed out is feedstock for the production of high strength permanent magnets. The Bear Lodge deposit and the material that we will be feeding to the demonstration plant includes almost all of the rare earth elements, and we will be collecting, or not, we won't be necessarily processing as part of the DOE project, but we will have available to us feedstock from heavy rare earths, SEG, etc., that we will be keeping on site. And should we decide to extend the project to produce additional materials using the technology that we have, then we should be able to do that. I mentioned the technology, and the technology that we're going to be using is solvent extraction, but it is proprietary. The methodology is proprietary to Rare Element Resources. As I said, we spent a lot of time and a lot of money developing this, and was recognized by the Department of Energy for the fine work that we did with regards to the pilot plant, and ready to move on to the next scale. I should say a few comments about our consortium. Our consortium consists of Rare Element Resources, another company called General Atomics. General Atomics is if it's not the largest, it's one of the largest private defense contractors in the United States. It is also our Rare Element Resources largest shareholder through an affiliated company. We also teamed up with a construction engineering company, which are providing those services to the project, and a fourth company altogether we call UIT. It's a German affiliate of General Atomics with expertise in technology, chemical processing, particularly as regards to recovery of critical materials around the world. So I think that put together a very, very strong team, and DOE recognized that, plus the technology, and granted us a very significant funding for this activity going forward. So let me check my notes here just a little bit. The demo plant will be fed by 1,000-ton sample that we have already acquired and is stored on private ground near Sundance. What that means is that we will be doing no mining on the resource that we've already identified up there. So there will be no permitting necessary with regards, or licensing necessary with regards to the mining activities, and there will be obviously there will be permitting and licensing required for the demonstration scale plant, but it is much smaller scale. So this 1,000 tons of material will be brought down from the mountain, and we will process that 1,000 tons at approximately 3 tons per day through the newly constructed plant, thereby absorbing about the 1,000 total tons as we move forward. The plant is expected to produce about 15 to 20 tons of NdPr oxides over the 1-year period that we anticipate that it will be operating. Again, having seen some of the questions and fielding numerous inquiries since we announced the demo plant and the associated funding that we're doing with it, you know, the activity is really meant to provide us with scaled up measure of performance of the demonstration plant, such that we will be able to use that going forward in the ultimate design of a commercial plant, assuming that we are successful and the board approves spending the money to do that. That would be the next step following completion of the demonstration scale plant. To kind of wrap things up here, let me just comment a little bit on the financing side of things for this project. As you know, Rare Element Resources is not a particularly large company, and we rely on going to the marketplace to raise funds for these kinds of activities. We're very fortunate that DOE has come forward with $20 million, $22 million of the total cost of the project. But on October 5th, in conjunction with the announcement of the DOE project, we announced that Rare Element Resources was going to launch what's called a rights offering. Rights offering to raise the additional funds. A rights offering is what you do with your existing shareholders. You provide them with a right to participate by acquiring additional shares of the company. In this particular case, our board of directors decided that it wanted to reward our shareholders who have been very, very good to us over a very long period of time. And so the rights offering has been priced at a pretty steep discount to the existing price to attract those our longtime loyal shareholders to continue to invest in the project and to move this project forward over the next 36 to 40 months. So anyway, that's a quick summary of where we are. I don't think that clearly a conventional rare earth project in many ways, and any small developing rare earth company with hopes of doing something special in Wyoming or any place else will go through many of the steps that we've had to go through in order to move forward with the hope that we're going to employ a lot of people and spend a great deal of capital in the state of Wyoming sometime in the future. So I wanted to thank you again for allowing me the opportunity to chat with you, and look forward to any questions. Thank you.
Randy, thank you so much. That was great. So again, we'll hold questions until the end, but Randy, thank you for your leadership. We're all pulling for you. Now, Tom, let's switch to you. Let's hear about some unconventional ways to get rare earth elements out.
Great, thanks, Scott. Thanks for the intro. So good afternoon and good morning, everyone. My name is Tom Tarka from the National Energy Technology Laboratory. We are located in Pittsburgh, Pennsylvania, Morgantown, West Virginia, and Albany, Oregon. Today, I'm going to talk to you about rare earth elements and other critical minerals in unconventional sources of those materials. I'll be focusing specifically on coal-related resources and unconventional resources, but these are broadly applicable to, this conversation is broadly applicable to other unconventional sources. Talk a little bit about the approach that we've taken at NETL's Research and Innovation Center to get there. Again, a little bit more background on myself. I've been lucky enough to lead NETL's research portfolio in the Research and Innovation Center for just over 4 years. So we have a great team of researchers at the lab, and that's part of the larger Office of Fossil Energy and Carbon Management Mineral Sustainability Program. So rare earth elements from coal. Unlocking this resource is challenging. It's an unconventional resource, and for a reason. We have really low concentration. If you think of traditional coal, conventional or traditional rare earth element related ores, you're talking about at the low end 0.5 weight percent, at the high end 50 weight percent of rare earth elements. Whereas in coal related feedstocks, AMD, we're down in the ppb range. Can we go back a slide, or I'm not sure if we're automatically moving forward or not. It might be, I might have screwed that up in my presentation I sent. So I don't know if you can go back a slide for me, Christine. But anyway, so we started off with a very low concentration resource. There are a lot of different coal is a pretty heterogeneous resource, and there's a lot of different potential permutations. Thank you. There's currently no domestic supply chain for the saleable product, so figuring out what we should be targeting in terms of concentration for our product is uncertain, and something that we've struggled with as we've looked at, where do we hand the product off, or do we have to take it all the way to a concentrated rare earth element material? And overarchingly, this is just a very broad problem. We almost have too many options with all the different coal-related resources, and which ones are, and to identify which ones are the best to target. Are the rare earth elements the product, or are you co-producing them? And so if you look at international producers, rare earth elements are frequently a co-product, maybe of iron mining or otherwise. Depends on the process, but that acts as a hedge for pricing and to risk. So next slide. If we think about the from the Research and Innovation Center perspective, this is our approach to addressing this challenging problem. First is kind of like what I call the how and the where. So let's find the best coal-related resources and then really understand them. And as you can see, that the high-quality resources are we kind of connote them by a combination of high concentration, ease of extractability, and abundant quantities. Making the numbers work. This is essentially making sure that we can compete economically with the international market, or working towards that, and identifying barriers and potential barriers beforehand, and then enabling domestic innovation. There are a lot of different things we can do to basically out-engineer our competitors, and we're looking at ways to do that, whether it's compressing development timeframes through using computational flow dynamic modeling, so we can scale from 1 to 10 as opposed to 1 to 5 at a time, or it may be just developing real-time sensors so we can do real-time process control. For that last bullet, I kind of think of it as, would you rather buy a first-generation Prius, or would you rather buy the current Tesla? So China has built out an extensive infrastructure and has a lot of capital outlay over the last 30 years, but maybe that can be used to our advantage by leapfrogging them in terms of the technology to go for. So one thing that people might not understand immediately, or might not think of with regards to coal-related resources and how rare earth elements occur in them, is the heterogeneity of those resources. And that goes from, the rare earth elements could be, for a given feedstock class, for coal ash, for example. In some ashes, the rare earth elements are encapsulated in a glassy phase, and in some resources they're not. So even, if we go from one coal to another coal, the rare earth element occurrences are going to be different. It can be different in the ashes. It could be different within a given even a different feedstock or the same feedstock class. So if we're looking at clays, underclays in Appalachia, we're finding a lot of variability. So that's really driven our need to develop characterization methods to understand the resources. Go to the next slide. Sometimes that means that we're taking over 600 different microscopic images, SEM images. So on the left, you see individual images from our scanning electron microscope. You can see how in different areas of the clay, there are different substrata in the clay, all of which have different rare earth elements occurring in different ways. Then if we stitch all of these images together, you can see more of the forest, and that's the image on the right, where you've got a lot of heterogeneity even within this clay material, and we can do element mapping. And so efforts like this allow us to better understand the resource and really inform extraction techniques and development techniques. Next slide. Similarly, we're developing cutting edge technologies and using our national laboratory capabilities across the national lab complex to go to the submicroscopic level. And what's really cool about this is my lead principal investigator on this tells me the X-ray that we're using in this is 100 billion times the strength of what you'd find in an emergency room or a hospital. So again, why is this important? By being able to understand down to the submicroscopic level how rare earth elements are existing in different resources. So what the oxidation state is, what they're binding with, et cetera, it informs our ability to develop extraction technologies that are cost competitive. And next slide. So all of these types of efforts have allowed us to develop a comprehensive resource assessment protocol. So we have a method of looking at individual materials, characterizing them, and working up the data in a way that's systematic. And next slide. And that's really going into helping to inform other efforts that we have, which are developing modeling frameworks and assessment methodologies that allow us to identify potentially high quality rare earth element or unconventional rare earth element resources. So this tool was developed by some of our folks out in Albany, and it's recently been rebranded as the URC, the Unconventional Rare Earth Element and Critical Minerals Resource Methodology and Assessment Methodology. And so the key takeaway from this is we're using geologic history and 21st century tools such as machine learning and big data and artificial intelligence to try to determine where we should look first for good resources, good unconventional resources. And some of you are aware of the Core CM award that came out of the DOE, and some of you are awardees on that. And these characterization methods and this assessment methodology are really meant to lay the foundation and framework for us to leverage all the data that's being collected across the nation and help us jumpstart this industry and figure out where we should start building potential, putting steel on the ground and developing these extracting resources. Next slide. Okay. So I'm waiting for it to load. There we go. So going into extraction research. Next slide. I'm just going to do. Some of these topics I could talk about for hours on end. So the key takeaways are that the DOE has performed a fairly extensive screening of different materials, unconventional materials, specifically with regards to coal, but we've recently broadened out into other unconventional materials like produced water and whatnot. And we've screened a number of conventional and traditional extraction pathways. The key takeaways from the last 5 or 6 years of these efforts are that it's technically feasible to produce high concentration rare earth elements from these materials. And you could say, well, of course it's technically feasible, but we didn't know that at first, and there was some question as to whether we'd be able to get to the quality of a traditional ore, or if we could get to that really high purity that you'd sell to someone, and we've been able to do that. So that's been a good first. That's been foundational. So we know we should be proceeding further. And this speaks a little bit to the previous presentation. What we found is it appears that downstream enrichment processes, maybe where we go from a 50% concentrate to a 90+% concentrate, or if we even separate our rare earth elements from a 90% mixed concentrate into individual elements or baskets, that these processes, as you get farther downstream, are more agnostic to the feedstock that you start with. And so when we talk about the Bear Lodge opportunity and that project, we might be able to link that in with other unconventional sources where we produce concentrates to send to their enrichment facility and therefore broaden the feedstocks that we're putting in and our resource base essentially. The other takeaway is, and I alluded to this before, economic viability isn't just tied to one factor, but it's really a combination of how easy is it to get the material out, the rare earth elements out, what is the starting concentration, And are you able to produce other things or get other value streams, whether that's tax credits, environmental cleanup credits, or actual products you're producing to hedge your economics. So in some cases, folks are looking at going into waste coal piles that were from 100 years ago, but have some metallurgical coal in them. And can we process that metallurgical coal, clean it up, and reduce the sulfur content, and in the process extract rare earth elements? So we have, in that case, the met coal is really the product, but the rare earth elements are the co-product, and you're really helping and strengthening your economics. So some feedstocks, and again, this is the level of this is just an overview, but in other talks, I would go through 3 feedstock classes that we've looked at, and one of them, acid mine drainage, is easily extractable. The rare earth elements are relatively easily extractable because you've had nature essentially doing all the extraction work for you. The problem is the concentration is very low. Another feedstock, such as certain ashes, your starting concentration is a lot higher because you've burned off all the carbon and you've essentially concentrated the rare earth elements into your ash in the process of burning it. The problem is that it's not as easily extractable, and it's going to require generally more chemicals, and in some cases, additional chemical processing steps to get the rare earth elements out. But it's a pretty abundant resource. Like I said, you're starting off at potentially north of 1,500 or 2,000 ppm, depending. And then some feedstocks, which are in the middle, would be like a particular underclay, where it's maybe more easily extractable than the rare earth elements in the coal ash, but maybe we're not able to get all of the rare earth elements out. So we have a lower total recovery, and the concentration may be a little lower than those ashes. So it's really a combination of all these factors, and we're working currently on building the economic assessment models so we can layer that into some of our prospectivity research and start looking at doing optimization cases for where you'd locate centralized processing facilities if you were to do a hub and spoke type build out for rare earth element production in different regions of the United States. Again, there are other factors, and that could just be how much is in a pile, how big is your pile, and do you have to drive down 500 miles of windy roads to get to a rail location or not, and all of a sudden your transportation costs go through the roof. Next slide. So where we are now, and this applies both to the portfolio that I lead and the larger FECM portfolio, which I can speak to a little bit. We started off and we said, well, can we use conventional ore processing technologies on unconventional resources? And so the answer is yes. And that's kind of the sledgehammer approach. So it's not looking at any innovation that's specifically geared towards these unique feedstocks, but it's just seeing, can we do it? So that's been validated at bench and pilot scales, and it's moving forward to demonstration. Similarly, we've validated novel and transformational processes that have been tailored specifically to unconventional resources. We started some field tests, and larger scale applications for that are being evaluated, or in some cases, industry is running with them on their own. So the broad goals here, of course, are the role of government research writ large is how can we de-risk deployment of these technologies and help industry move forward in areas where there's too much risk for people to move forward on their own. And this last bullet, just in general, our focus is really how do we get these technologies out the door? How do we compress these development timeframes and help stand up an industry as rapidly as possible? Next slide. This is just a quick overview of one of our extraction technologies with some Wyoming connections. And so the short version here is, and just high level, some traditional rare earth element processing processes require really intense process conditions. They're performed at temperature and pressure and use very acidic or caustic chemicals. And so our focus has really been, and this program is focused for large, is reducing those environmental impacts and trying to operate a little smarter, not harder. So this is just an example where we've identified a particular type of ash, calcium-rich ashes, such as those found in the Powder River Basin. And it's different enough from other ashes that you don't have to process it as much, and we're able to get the rare earth elements out without dissolving the whole. For a pound of ash, instead of having to dissolve all of that ash, we only have to dissolve a portion of it, which drives down the amount of chemicals we have to use. So, next slide. And to that extent, we actually were awarded a technology commercialization fund project for Wyoming that we're working with the School of Energy Resources on. They're one partner, as well as Campbell County and the City of Gillette. So we're really excited that we're moving forward and setting up a very small pilot plant that should be up and running in, I want to say, 20 months or so. Next slide. The other piece of enabling domestic innovation and kind of breaking some of these barriers is really understanding the economics and process considerations. This helps us inform where we should spend more research dollars and whether we should continue to fund different projects. We're also really starting to get into, this has been a big push for the current administration, but something that we've been interested in a long while, which is life cycle analysis. So it doesn't help to produce rare earth elements if you're doing a lot of environmental damage to begin with. And some of the current processing in China, the processes have done a lot of environmental damage, and generally that supply chain is pretty opaque. So there's movement to integrate that more into the assessment of these materials, including efforts being led at the ISO, the International Standards Organization, for rare earth elements and also lithium production. The other thing, and this is just putting on my systems engineer hat, we've been doing a lot of process or techno-economic analyses to do process screening. We really want to help identify what the real challenges to each project are before we start sinking money into it, because that can compress our time frame and cost. Next slide. Also, with regards to enabling domestic innovation, there are key pieces that are missing, or technology gaps that are missing in current rare earth element processing. This is one example where generally, if you're going to analyze a material for rare earth elements, the process could take hours or days, because you have to send it off for an ICP, inductively coupled plasma mass spectrometer analysis, or spectroscopy analysis. And so the result of this is you can't do real-time process control. So a lot of these rare earth element processing facilities in China, you've got 100 different stages or thousands of different stages, and it takes you a week to get it up and running and get it to steady state. And once it's at steady state, you don't touch it, because you have no idea what's going on in the process, and any perturbation can impact the purity and the spec of your product. And so we've been successful in, this is an area we identified of, can we do real-time measurements? If so, maybe that will now allow us to do real-time process control and make our processes more efficient, or innovate otherwise in separations processes. So these are other areas that there's a key need for. New alloy development is another one that our portfolio is looking at, and others are looking at as well. Next slide. And this is just to wrap it up. And again, I could talk about a lot of these topics for hours, and I encourage you to reach out if you have any questions, thoughts, or considerations. But this is a rapidly evolving area. The program has, the FECM program has really been amazing, in the sense that just 6 years ago, we didn't know if we would be able to produce high purity rare earth elements and rare earth element oxides from unconventional resources. And we've done that, and we've got a much better understanding of the resource. And now we're continuing to develop the process to understand where the resource may be, we're using new and novel 21st century methods to simulate processes and optimize processes. And we're really trying to reach across all of the domestic stakeholder base to all work together, whether it's through sharing data, or through help in commercializing, or just outreach to rapidly deploy these new technologies. So I probably have gone over time, for which I apologize. And thank you very much for your attention.
Tom, thank you very much. And Jada, the floor is yours.
Thank you, Scott. All right. It's a pleasure to participate today. My name is Jada Garofalo. I'm with the School of Energy Resources, particularly the Center for Energy Regulation and Policy Analysis with the University of Wyoming. My talk today will just provide a high-level overview of the law and policy impacting rare earth elements and critical minerals in Wyoming and more broadly. Next slide, please. So you'll see here just a brief overview of what I'll go over. First, I will cover how critical minerals and rare earth elements are defined. Then we'll discuss the law, both federal and state, discuss where we are today and some recent movement in the law, and then some challenges that we face. So let's advance to the next slide and we'll turn to how critical minerals and rare earth elements are defined. So you can advance again, please. Thank you. So as increased demand for critical minerals and rare earth elements was recognized, one of the first actions that was taken was to formally define critical minerals and rare earth elements. So you'll see here, President Trump's Executive Order 13817 in 2017 defined critical minerals as minerals identified by the Secretary of Interior that are non-fuel minerals essential to the economic and national security of the US, minerals with a supply chain vulnerable to disruption, or minerals that serve an essential function in the manufacturing of a product, without which would have significant consequences to the US economy or national security. Next slide, please. In early 2018, under direction of this executive order and in coordination with the BLM, the USGS published a list of 35 critical minerals. That list is here on this slide, and as you can see, rare earth elements are a subset of critical minerals. If you advance again, you can see here the 17 rare earth elements. These are elements depicted here by their atomic weight. They are not actually all that rare, but they are hard to locate in economic deposits. And importantly, the bolded rare earth elements on this slide are called critical rare earth elements. And while the critical rare earth element list may change from time to time, critical rare earth elements are more sought after and in demand than the rest. Next slide, please. As you can see here, the recently signed Infrastructure Investment and Jobs Act signed by the House on November 5th adopted the definition of critical minerals in the Energy Act of 2020, which was passed as part of the Consolidated Appropriations Act in December of 2020. Next slide, please. The Energy Act of 2020 defined critical minerals as any mineral, element, substance, or material designated as critical by the Secretary of Interior under subsection C. So next slide, please. What does subsection C say? It specifies the procedures and processes the Secretary of Interior must follow to make and add to the list of critical minerals. And critical minerals were covered as byproducts, which is in line with that original Executive Order 13817. Subsection C also requires that the USGS review and revise the methodology used to evaluate the mineral criticality, as well as the list itself, no less than every 3 years. In line with this evolving process, the USGS published recommended updates on May 7th of this year, and the revised list was actually published last Tuesday, November 9th, and is now open for public comment through December. If we advance to the next slide, you'll see we're going to turn now to federal mining law. Next slide again. Thank you, Christine. Minerals on federal lands are divided into 3 categories, each subject to different laws and regulations. So first we have what are called locatable minerals. These are subject to the General Mining Law of 1872. These typically include both metallic and non-metallic metals. So gold, silver, lead, copper, mica, certain limestones, gemstones, and others. Then we have the leasable minerals. These are subject to the Mineral Leasing Acts. These typically include coal, oil, gas, shale, geothermal resources, potash, bituminous rock, phosphate, and others. Then we have saleable minerals. Saleable minerals were removed from the General Mining Law and placed under the Materials Act of 1947. These typically include gravel, sand, stone, pumice, and cinders. So it might take a minute to load, but you can advance. I think it's 4 times. I didn't think this through. Okay, so the important thing to note here I'm not going to go into detail, but it's important to know that Wyoming has large quantities of minerals in each category, and that critical minerals are typically found in the locatable mineral deposits in rock and are thus subject to the General Mining Law of 1872. Next slide, please. So the General Mining Law of 1872 applies to mining claims on federal lands. We're next going to take a look at each aspect of the components of the law. So first, what federal public lands are open to mineral development. Second, what is a valuable mineral deposit? Third, what is the process to stake and maintain a claim? And then finally, what right is afforded? Next slide, please. So 19 states have federal public land open to mineral development under the General Mining Law, depicted here in green. The BLM manages subsurface minerals on both the BLM land and the U.S. Forest Service land. In Wyoming, just under half the state, around 48%, is federal land. But not all federal lands are open to mineral development. Some federal public lands have been what's called withdrawn from mineral entry. For example, national parks and monuments depicted in the right-hand map in purple, reclamation projects in pale yellow, military land in brown are all withdrawn. Other withdrawn land may include wilderness preservation systems, scientific testing areas, wildlife protection areas, and maybe wildlife refuges. Lands purchased or received under the Acquired Lands Act of 1947 or found on tribal lands are typically subject to lease, and tribal lands here are depicted in orange. Next slide, please. The General Mining Law uses the term valuable mineral deposits, but it does not define that term. Courts have used tests to determine what a valuable deposit is. The Prudent Man Rule was first stated in Castle v. Womble in 1894. It states that a person of ordinary prudence would be justified in expending labor and means to explore a mineral deposit. The U.S. Supreme Court approved that rule in Crispin v. Miller in 1905. The Marketability Test was used in U.S. v. Coleman in 1968. This test is supplemental to the Prudent Man Rule and considers deposit economics along with market entry. So in this case, a claimant must show a reasonable prospect of making a profit from the sale of minerals. Next slide, please. So staking a claim and maintaining that claim. The General Mining Law allows states to establish their own laws for locating, recording, and maintaining a claim with the state. So the claimant must meet both the federal and the state requirements here. Typically, the claim and site boundaries must be distinctly and clearly marked to be readily identifiable from the ground. Next slide, please, and you can advance twice total. So the right awarded can be either an unpatented or a patented mining claim. Ownership of a valid unpatented mining claim awards the exclusive right to possess a select parcel of federal land for the purpose of developing and extracting valuable mineral deposits, whereas a patented mining claim results in exclusive fee title or ownership. Historically, the option to patent a mining claim opened much of the U.S. to lands to exploration, settlement, and eventual purchase, sometimes based on questionable deposits of locatable minerals. Advance once more, please. So effective October 1st, 1994, Congress imposed a moratorium on spending appropriated funds for the acceptance or processing of mineral patent applications. Until the moratorium is lifted or otherwise expires, the BLM will not accept any new patent applications. So yes, that's supposed to just be a cross over the patent application. This is a list here of other federal laws that may be implicated by mining projects, and it's not exhaustive in any way, but it does list some of the important ones. A project may include these or others. I'm only going to discuss 3 important ones here today. First, NEPA. NEPA established an environmental process for evaluating and communicating the environmental consequences of federal agency actions, and NEPA applies here to mining operations that require federal approvals. RCRA prevents the release of hazardous wastes into the environment by providing for management from generation through till disposal. Subtitle D deals with non-hazardous solid wastes, and Subtitle C deals with hazardous solid wastes. Fossil fuel combustion wastes like fly ash, bottom ash, boiler slag, and particulates removed from flue gas were all excluded from regulation under Subtitle C, but are instead regulated under Subtitle D of RCRA, dealing with non-hazardous solid wastes, under the coal combustion residuals regulations. Certain wastes from production of oil, natural gas, and geothermal energy were also excluded from Subtitle C of RCRA. And most mining, milling, and smelting solid wastes are called high volume, low hazard materials and are thus exempted from regulation under RCRA, and instead are the primary responsibility of the states. The rest of mineral processing wastes are typically regulated under RCRA. Finally, CERCLA. This law enables the federal government to clean up any site where there is an unremedied release of a hazardous substance. But in the case of CERCLA, hazardous substances are broadly defined, and they may include mining, milling, and smelter wastes, which are excluded under RCRA. Regulators have authority to use special funds and to hold all historic owners or contributors liable for the cleanup costs, with liability broadly defined. Let's now turn to state mining law. If you could advance 2 slides, please. So on top of those federal laws that we've just discussed, Wyoming also has its own mining, siting, environmental, hazardous materials, and reclamation laws that apply in tandem with federal laws. For instance, the Wyoming Constitution allows for taxation of valuable deposits. If you could advance twice more, please. You'll see here a list of regulations that may apply to a mining project in Wyoming. In Wyoming, solid mineral leasing on state lands is guided by Wyoming Statute 36.6101 and chapters 19 through 25 of the Rules and Regulations of the Board of Land Commissioners. In particular, chapter 24 details procedures for metallic and non-metallic rocks and minerals. And these processes include leasing, royalty calculation, reclamation obligations, bonding and reporting requirements, as well as the practice of auditing and ensuring multi-use. Importantly, no mining may occur without a valid mining permit or a valid license to mine for minerals. A license is a certification that the licensee has the right to conduct mining operations on the lands, has deposited a bond, and the administrator has determined that the licensed mining operation has a valid purpose. The Wyoming Department of Workforce Safety conducts inspections to ensure mine safety. The Wyoming Department of Environmental Quality oversees 3 divisions related to mining. First, the Land Quality Division, which regulates the licensing, applications, and permitting for all non-coal mine production in the state. Second, the Industrial Siting Division, which assesses socioeconomic and environmental impacts for companies planning major industrial developments. And third, Solid and Hazardous Waste Division, which protects the health and the environment by ensuring proper management of those solid and hazardous wastes and promotes reuse of materials for sustainability. So now let's turn to where we are today. I'm going to discuss here very broadly the 3 main executive actions that have occurred, agency action very broadly, and then some recent legislative efforts. You can sort of follow along on this slide, although I apologize that the light green is hard to see. So President Trump's first executive order that we've already discussed a little bit was released in December of 2017. It announced the policy of the federal government was to reduce the nation's vulnerability to disruptions of the supply of critical minerals. It set out a formal definition for critical minerals, initiated a process for continual evaluation of the list, and specified actions to take to evaluate the extent of the vulnerability and to establish a domestic supply chain. President Trump's second executive order, 13953, in October of 2020, was more forthright. It stated that critical minerals are indispensable to our country. The United States lacks the capacity to produce them in processed form in the quantities needed, as we've heard earlier today, and that China has used aggressive economic practices to encourage industries to locate their facilities and technology in China. It also set up a repetitive reporting process by agencies to the president on the state of the threat posed by national reliance on a foreign supply. President Biden also issued an executive order, number 14017, in the beginning of his presidency in February, which set out the policy of his administration, which is to strengthen the resilience of America's supply chains. This executive order required a 100-day supply chain review and required the DoD to identify risks in the supply chain for critical minerals and policy recommendations to address those risks. You'll see here that agency action is largely focused on funding both research and commercial development, indicated in this slide in orange and blue squares. And as for recent legislative action, the Energy Act of 2020, passed in late December of 2020, requires the Secretary of Energy to carry out a research and development program for the extraction and recovery of rare earth elements and critical minerals from coal and coal byproducts, as we've heard earlier from Tom. to promote a secure and robust critical mineral supply chain, and to monitor mineral investments by China. The Infrastructure Investment and Jobs Act passed last week includes appropriations for research facilities, demonstration facilities, programs, and commercial development facilities. So we are seeing continual funding for this. Next slide, we'll discuss finally the challenges faced. So there have been proposals to reform NEPA as it relates to critical minerals to address the burdensome system of permitting for mining projects, some suggesting specific timelines for permitting as short as 24 months, which would really speed up the process for permitting. There have also been proposals to reform the general mining law and implement leasing and royalties programs, like the mineral leasing acts that apply to coal and gas development on federal lands. Many argue that the law was created in 1872 to encourage settlement of the West and that the law no longer reflects present-day usage. There have been numerous attempts to amend or repeal the general mining law of 1872, the most recent of which was proposed in the October 28th House Committee revision of the Build Back Better Act, which is written would have added a 2% royalty on any mining claim, concentrate, or product derived from locatable minerals on federal lands, but the House Rules Committee revision on November 3rd struck that royalty provision. Given the importance of critical minerals to both the national security and energy, and the fact that they tend to fall under the general mining law, I think it's safe to expect continued attention on the general mining law in years to come. Regarding unconventionally sourced critical minerals, because as the law is now, the mineral type, locatable, leasable, or saleable, currently determines the applicable law for sourcing, a current challenge is figuring out how to regulate unconventionally sourced critical minerals. Some byproducts are regulated under RCRA and some are regulated by states, so it does remain unclear which laws would apply and also how the applicable laws would need to change in order to source critical minerals from recycled sources, fossil fuel combustion waste and byproducts, and waste and byproducts of industrial processes. As further funding is directed towards researching the potential to recover rare earth elements and critical minerals from unconventional sources, it's suggested that modifications in the law are also studied in tandem to facilitate this type of sourcing. So next slide, and I'd like to thank you for your time and welcome any questions.
All right, thank you, Jada. Aaron, let's go quickly to you. Keep us on time.
All right, thank you, Scott. My name is Erin Phillips, and I'm a senior research scientist here at the School of Energy Resources. And today I'll be talking about opportunities for rare earth element development in Wyoming. Next, please. And just a note here, portions of the following slides describe work supported by the Department of Energy. So this disclaimer just states that the views and opinions in this presentation do not necessarily reflect those of the US government or any agency thereof. Next, please. So today I'd like to talk about the importance of Wyoming's energy and mining infrastructure for future rare earth element development in Wyoming. Talk about established research, technology, and economic development programs in the state. Give a brief overview of rare earth element resources in Wyoming, and wrap up talking about a couple new initiatives that we have here at the School of Energy Resources under the Core CM program. Next, please. So Wyoming has a well-established energy and mining infrastructure. More than 40% of the coal produced in the United States comes from Wyoming, and the original coal resource in the Powder River Basin alone is estimated at about 1.1 trillion short tons. Wyoming coal is shipped to power plants in 29 states and utilized in 113 coal-fired electricity generation units. So this means that Wyoming resources represent a significant amount of the coal byproduct resource across the country. Low production costs for Wyoming coal due to surface mining and mining techniques and thick coal seams can improve economics of potential rare earth extraction from carbon ore. Next, please. Additionally, Wyoming ranks among the top 10 states for both crude oil and natural gas production and leads the US in bentonite and uranium production. And Wyoming hosts the world's largest trona deposit. Wyoming's renewable energy portfolio includes rapidly expanding wind power generating capacity, as well as hydroelectric and solar resources. So all of this is really to say that Wyoming is home to an established energy infrastructure, motivated stakeholders, and a highly trained energy and mining technology workforce. Next, please. Rare earth element research has been taking place for the last several years at the University of Wyoming School of Energy Resources within a number of our different centers of excellence. So here at the Center for Economic Geology Research, our group is made up of geologists and engineers, and who, among many other things, are focusing on the characterization of rare earth element and critical mineral occurrence across Wyoming. I'll talk more about Core CM later, but our group has also collaborated with the National Energy Technology Laboratory to study rare earth elements in coal and coal byproducts. We've been very fortunate to work with Tom Tarka, Kelly Rose, Scott Montross, Bert Thomas, and their team to contribute samples and analyses of Wyoming coal and coal byproducts to broader resource assessment efforts. We also collaborate with the University of Wyoming Department of Geology and Geophysics, as well as faculty and staff from across campus, as well as the Wyoming State Geological Survey, who publish many valuable much valuable work on rare earth elements and critical minerals. We've also been very fortunate to collaborate with industry stakeholders across the state, which provide invaluable insight into not only coal and coal byproducts, but other mining products. Other centers of excellence here at the School of Energy Resources include the Center for Energy Regulation and Policy Analysis and the Center for Carbon Capture and Conversion. The last center there has been studying the unique properties of Wyoming coal for a number of years and how it can best be utilized in carbon ore products. In addition, there is much other state and federal funding coming into rare earth element research and critical minerals research currently, and other projects that have been completed in the recent past. So the emphasis here is that there is a strong base for rare earth element research in the state and momentum around continuing this research. Next, please. In addition to this research, there's also a strong technology and economic development base in Wyoming. Examples of technology centers that are field testing energy technology in the state include the Wyoming Innovation Center, which is located in Gillette. This is a public-private research to commercialization facility designed to conduct scale-up research for rare earth elements, critical minerals, and advanced carbon products. Ramaco's Carbon Advanced Materials Center in Sheridan will host bench to pilot scale applied research projects aimed at commercialization of coal-based products. And the Wyoming Integrated Test Center, located outside Gillette, is a public-private partnership designed to investigate commercial uses for carbon dioxide. So these established centers really provide a roadmap for continuing work in this area and establishment of new technology centers in Wyoming. Economic development and other statewide programs also provide support. This is certainly not an exhaustive list, but good examples include the Carbon Valley Initiative in Campbell County, the Upton Economic Development Board, and the Sweetwater Economic Development Coalition. Additionally, community colleges across the state provide workforce development programs around the energy industry. And statewide programs are also providing support for emerging industries, including the Wyoming Energy Authority and the Wyoming Business Council. Next slide, please. So I would like to briefly just talk about some rare earth element resources in Wyoming, and we've already talked about a number of these, so I will be brief, but I'd like to draw your attention to the reference in the lower right-hand corner, which is from the Wyoming State Geological Survey. Sutherland and Kola 2016 provides a good, a lot of good information about rare earth element resources in Wyoming. Next, please. So as Tom already spoke about, rare earth elements in coal. Coal is a potential unconventional source for rare earth elements. We have been looking at, with our project partners, to characterize the geochemistry of Wyoming coals and to better understand their distribution in coal systems. These studies are really helping us to better characterize coals and show us that rare earth elements are often distributed in a predictable way. Industry partners provide invaluable access to mines, coal core, and insight into mine geology. Coal core is especially useful because it helps us to understand the rare earth element distribution in a vertical sense within a coal system. So the example on the right here shows rare earth element concentration with depth in a particular coal core that we analyzed. And here we're seeing some bounding enrichments at the bottom and the top of this coal seam. And that's something that we often see in these coal systems. So this is not necessarily the only method or the only mode of enrichment, but we are investigating this type of enrichment as well as others and the mechanisms by which they occur. Next, please. Coal ash is also a potential unconventional source of rare earth elements. And we are looking at the geochemistry of coal ash, and that's helping us to understand differences between in the geochemistry of coal ash between basins. The plot on the right there shows you the differences between Powder River Basin and Green River Basin coal ash. And as Tom also noted earlier, some of these rare earth element extraction techniques are being investigated in a technology commercialization fund project in the Powder River Basin. And we're collaborating with the National Energy Technology Laboratory, Campbell County, the City of Gillette, and Energy Capital Economic Development on this project. And feel very fortunate to be working with Tom Tarka, Christine Lopano, Mengling Stuckman on their team, working on testing, optimization, and eventually demonstration of rare earth element extraction techniques. Next, please. Other rare earth element potential in Wyoming, we've talked about the Bear Lodge deposit. This is one of the largest conventional rare earth element deposits in the US. It is a carbonatite complex. Rare earth elements occur in other igneous and metamorphic rocks across Wyoming, including pegmatites, other carbonatites, and alkaline igneous and metamorphic rocks. Placer and paleoplacer deposits form when water or gravity separate minerals from surrounding materials. So these could form potentially downstream from a rare earth element bearing source. Sedimentary phosphates are a potential source of rare earth elements, and the Phosphoria Formation in Wyoming contains sedimentary phosphates. And last, uranium and rare earth elements sometimes co-occur, and the mechanisms by which this occurrence, as well as sedimentary phosphate and rare earth element co-occurrence happen, are being investigated at the University of Wyoming Department of Geology by faculty and students there in collaboration with SER, with the School of Energy Resources. Next, please. And an important focus of rare earth element research currently is the potential for rare earth element concentrations in existing waste streams. And that could provide value added benefits to Wyoming industries because they're already producing these waste streams. We've already talked about coal ash. Oil and gas produced waters are another waste stream produced in Wyoming. The School of Energy Resources did an initial study on these waters and found that rare earth element concentrations were in the parts per trillion level, which is currently well below economic values. The other waste streams listed here require further study to determine their rare earth element potential, but need to be considered and include waste streams associated with bentonite, trona, and uranium mining industries, as well as hard rock mine tailings. And thinking towards the future and the build out of potential rare earth element infrastructure, Wyoming could have opportunities with relation to rare earth element recycling. And this research also provides synergies between fossil and renewable energy industries. Next, please. And I'd like to kind of bring it back here to the supply chain that Holly talked about in the beginning of the webinar. And I won't spend too much time on here, but just to say that the supply chain for rare earth elements and critical minerals as well is quite complicated and involves a number of steps. There's a lot of work going on in the exploration and mining upstream part of the supply chain, but it is very important to develop each piece of the supply chain for domestic security. And the take home here really is that opportunities for development exist around all parts of the rare earth element supply chain. Next, please. And I'll wrap up by talking about the Core CM initiative, or Carbon Ore, Rare Earth and Critical Minerals Initiative. This initiative is funded by the Department of Energy and focused on catalyzing basin-wide economic growth and job creation around all parts of the core CM value chain. 13 core CM projects in traditionally fossil fuel producing regions were awarded in 2021. The School of Energy Resources is leading 2 of these projects, one in the Powder River Basin of Wyoming and Montana, and one in the Greater Green River and Wind River Basins of Wyoming and Colorado. Each project will receive about $1.5 million in federal funds, with cost share provided by the School of Energy Resources, the Wyoming Energy Authority, and other project partners. Next, please. There's 6 areas of focus within each project. So we'll be looking at core CM resources, the reuse of those waste streams that I spoke about, strategies for infrastructure and industries, technology assessment, looking at plans for technology innovation centers and ways that we can support existing centers, and strategies for stakeholder outreach and education. So that will focus on development of workforce training plans with community colleges. There are a number of opportunities for engagement with the core CM projects, including stakeholder forums and workshops and online data sharing and educational content. One of the main parts of these projects is to build a network of stakeholders that can talk to each other about each part of that rare earth element and critical mineral supply chain. So I would encourage you to contact myself or Davin Bagdonis if you would like more information on how to be involved in these projects. We welcome project partners from anyone interested in research and development in the rare earth element or critical mineral or carbon ore development areas. I'm leading the Powder River Basin proposal, and Mr. Bagdonis is leading the Greater Green River and Wind River Basin project. So next slide, please. And here I've just listed some resources for more information. This will be available in the recorded version. And next slide, please. And thank you very much.
All right, and thank you, Erin, and thank you to all of our panelists. We are running short on time, but we did have some great questions come in. So why don't I ask you guys a few questions? So one big picture one, and I'll let the panelists jump in on, what is the single biggest hurdle in getting rare earth element or rare earth mining moving forward in Wyoming? Let's break that. That's a big question. How about we just send it to the, let's say, what are some of those hurdles out there that we need to be addressing? What are some of those research gaps?
I mean, part of the issue is having a market pull. And so I think particularly for unconventional resources, we need to be producing these high purity materials from these unconventional sources and handing them off to potential end users, whether those are magnet producers or otherwise, so that they can test and validate that these materials are viable in their processes. And so anything that we can do, we're also looking, as a DOE employee, I can inform policy, but can't set policy. I have to be a little careful, but I think we're trying to engage with industry to let them know that we're here, that we have potential new sources of these materials, and to better understand what their exposure is. Because I think from a project financing perspective, if we can do some matchmaking and make sure there's market pull, that just helps everybody.
All right, great. Thanks, Tom. So let's talk about environmental and social justice. What considerations are being made for rare earth element mining? And yeah, any comments on environmental and social justice?
I can comment on that, Scott, with relation to the core CM projects at least, and likely this will be applicable to most federally funded projects for the core CM projects, we are required to basically provide a deliverable to the Department of Energy that addresses environmental and social justice issues. So this will be a document that describes how the projects will incorporate community and stakeholder input and engagement from underserved communities. And it will also look at any additional waste streams that may be produced by these industries. It will look at legacy environmental impacts, look at any new technologies and their environmental impacts. And also, I think that it also addresses kind of social license to operate with relation to these projects. Stakeholder engagement is very important, and that's a central part of any of these federally funded projects.
So I want to be respectful of everybody's time. So if I circulate these questions with the panelists, could you guys take a stab at them and we'll make sure we get them on our website? But I have one more question I just want to throw out to the group. I just lost it, I apologize.
I may have answered it by typing, in which case I don't know if I did and it disappeared.
Thanks, Tom. It may have disappeared from my list here. So let me pick one more. And Randy, I think you answered this in your presentation, but can you just give us the 30-second overview of where the Bear Lodge deposit development stands from a permitting and financial security perspective, securing finance perspective?
Yeah, sure. As I introduced the presentation, I drew the distinction between the commercial project and the demonstration plant. And what we're really focused on now will be the successful engineering, construction, and operation of the demonstration plant. And again, we've been quite fortunate to have convinced DOE to fund that to the tune of $22 million. And now we're out trying to raise another $22 million for the total cost of that demonstration plant. So I think that the focus over the next year or two is going to be on completing success in that demo plant, which will then inform the final feasibility study for the commercial plant going forward.
All right, thank you. So thanks again to all of our panelists. You guys all did a great job. We are at time, so I will let you go. But just a reminder to everybody out there, we will post this on our website and we will follow up with the answers to the other questions that we weren't able to answer. So with that, we'll close the session. Thank you, everybody.
Thank you very much.
Thanks, everybody. It's been great to participate with all of you.
Same, thank you.
Thank you.